Well, thank you, folks, for coming. I imagine we'll have folks drifting in and out. We've got an ambitious schedule over the next 2 hours to go through. So I hope you'll bear with us, because I think there'll be a lot of fun parts to this celebration this afternoon. So we'll jump right into this. First thing I want to do is highlight some of the prior events of our research celebration. First one shown here occurred last Friday afternoon. I had the privilege of attending some of these presentations. It was really quite impressive. But I did just want to highlight that in the postdoc division, first place was Gabriella Vicini, runner-up Kirsten Tracy. In the senior graduate division, first place was Dominic Lassard, runner-up Devin Champagne. And in the junior graduate division, Leslie Sapaniak was first place, and runner-up was Alec Thompson. So we just have a quick hand for these folks if they're here. And then earlier today at lunch, I know many of you were at this presentation, but if you weren't, you really missed out. David Warsaw gave a wonderful talk titled Networking and Personal Branding, Two Keys to Success. And this was part of his recognition with the 2017 UVM Medical Alumni Association Distinguished Graduate Award. And David, I guess I learned today he actually got his PhD in 78. We keep jumping back and forth. It's either 78 or 79. But he is an alumnus and professor and chair of molecular physiology and biophysics department. And of course, he's widely recognized for his work at the cardio lab. But anyway, it was a wonderful presentation, and I'd like to have a quick hand for David as well. So this is the agenda for the afternoon. Next will be Dean Morin's going to just give some welcoming remarks. Then I'm going to do the sort of state of the research in the college address, probably 20, 25 minutes at most, so just an overview of where we are today. Then we're going to do the Dean's Excellence in Research Awards. The first ones will be the trainees, followed by Claude Deschamps is going to give the UVM Health Network Medical Group Awards. And after that will come our faculty awards. Now, just to give some instructions, what we'll do when we get to the awards, and we'll probably repeat this, will be for the, we'll announce the nominees, then I'll announce the award recipient. And the award recipient and their mentor, or whoever's covering for the mentor, will come down to receive the awards. We'll shoot a quick picture, and off you go. With the faculty awards, we do that, we'll have the, again, the award recipient come down, and if the person who nominated them is present, they can come down as well. And again, we'll shoot a quick picture. We're giving a lot of awards, so we're going to try and do this like you do almost a college graduation. So we'll kind of crank people through here as best we can, so no speeches or anything like that. Now, also afterwards, if all the award recipients, both the trainees and faculty, can head over towards the courtyard, we're going to shoot some pictures over there as well. And all this fun will be followed by a wine and cheese reception over in the whole gallery. So we've got a busy agenda ahead, and I'll turn it over to Dean Morin for some welcoming remarks.
Well, good afternoon. Let's see. Am I getting them? No, we're good. I think we're good. I think we're good. We got it aimed away. Well, good afternoon. I'm Rick Morin, Dean of the Larner College of Medicine, and I'd like to welcome you all to our second annual Celebration in Research Excellence Awards. I welcome both those of you who are here with us in the audience and those who are across the region and beyond on our live stream. This event has grown out actually of a strategic planning process we did two and a half years ago that said we needed to really improve the position, the recognition, and of our accomplishments in research here. And Gordon put together this really several days of recognition exercises for us. And I'm really pleased that so far this, as you've heard, this celebration has included this last Friday, the work of the graduate students and their mentors. And then earlier today, an outstanding alumni scientist, our own David Warshaw, who gave a great talk. And this afternoon, research excellence across the Larner College of Medicine and the faculty of the University of Vermont Health Network. And we're here today to acknowledge the scientific inquiry taking place throughout our institutions and its partners, and the important mentorship and training that create the future of a vibrant research institution. A successful research institution doesn't just happen by accident. It takes really thoughtful planning and hard work and commitment. And here today, we're really celebrating the vision and the dedication of the members of our research community and the results thereof. And so I'm really glad to share that we can share this day and hear from our distinguished guest, Dr. John Lorsch, from the Director of the National Institute of General Medical Sciences. And now I'd like to turn the podium back to Gordon Jensen, our Senior Associate Dean for Research, to give a deeper view of the research going on here at the Larner College of Medicine.
Okay, well, as I said, I'm going to give you a brief overview of where we are today in the college on our research trajectory. Anyway, I do want to start by saying good things are happening that I want to share with you. It certainly is not all doom and gloom. And in fact, many of our research performance metrics are really quite favorable. And first one I wanted to highlight, I put the department heads through this big ordeal every year of forwarding all the publication information. We do it for a reason. It's a very important metric to us. And you can see that this past year, we actually set a new college record for peer-reviewed publications, 1,168 papers, which for a college of this size is actually quite impressive. You really are all to be congratulated. Similarly, on the funding front, we continue to fluctuate between $70 and $90 million annually. And then the next bullet, I think, is a plus. There's some that might question it for little state of Vermont. But one of the consequences is that we are actually among the top 10 states per capita in federal research funding. These are the major grant awards by investigator for the college this past fiscal year. You can see that Dr. Higgins is here, third actually. Dr. Shaw, Dr. Kirkpatrick, Dr. Walsh, Dr. Callan, Dr. Budd, Dr. Caravan, Dr. Lewis, and Dr. Jensen Heiniger. And this is really quite remarkable. We have multiple individual, very accomplished, well-funded investigators here at the College of Medicine. We've also had multiple COBRAs, really quite timely, given that Dr. Lorsch is visiting today, since he's come from his Institute of General Medical Sciences at NIH. We've had the Lung Center, the Neuroscience Center, Immunobiology and Infectious Disease, the Center on Behavior and Health. These are all, some are sundowning, some entering phase 2. But the big brand new grant that I did want to share with you is the CTR grant, the Northern New England Clinical and Translational Research Grant that Gary Stein and I brought in July of this year, again from Dr. Lorsch's institute. So this was awarded July 3rd. It's a 5-year, $20 million grant from NIH with our partners in Maine. And so working with Gary and myself, Cliff Rosen and Tom Ridley at the Maine Research Institute in Portland. This is a regional consortium focused upon rural health across the whole northern tier of England, so Maine, New Hampshire, and Vermont, with a goal of really promoting health of the people of northern New England and fostering, supporting clinical, translational, educational research activities across northern New England. I primarily share this today because I wanted to highlight some opportunities for you that come with this. Now, don't worry about this complex figure. It's kind of cute. They actually focused on our core directors and co-directors are all in green. The main ones are in red or blue. Anyway, you'll recognize a bunch of the names here. We have multiple cores in this to support research, education, training. And so you can see we've got Tom Peterson, Patty Prelock on the advisory committee, Kim Movers in professional development, pilot projects, Jane Leanne, Bernard Cole in research design and epidemiology, Fran Carr in translational research technologies, Jan Carney in the rural health research and delivery core. Charlie McLean also has a key role there. So you can see this major grant is really a very collaborative undertaking shared with our partners in Maine. Each core has Maine and Vermont partners. But this was the opportunity that I wanted to share with this, and some of you may have seen. Just this fall, we sent out the very first pilot funding announcement. We really put a lot into rolling this out very quickly. We've got a website going up. Anyway, the first request for proposals went out. We had received 35 letters of intent. We have 11 full proposals in review currently. The awards will be announced in early December. So that cycle is already rolling forward. But I did want to highlight for you that another cycle will be initiated in the spring. Hoping to do at least 2 cycles per year. So keep an eye out for that, because that will go out as an email announcement. It will also be on the website. And I should add that this is, we're getting proposals that are mechanistic research, translational research, and every permutation thereof. So it's not just about, clinical research in the field per se. So this was actually a slide I used in last year's State of the College address, just at that point, highlighting some of the ongoing strategic programs and investments. And so what I hope to do for you this afternoon is show where we are with many of these things, because I hope you'll take away that there really is an awful lot going on. So the first one, in health services research, one of the major strategic priorities was the development of a new health services research center. We've got a host of collaborative partners, including the Medical Center and the Health Network as key partners in this. It's one of the strongest alignments of interest that we have with the Health Network and the Medical Center. We had budgeted $2.5 million startup from the College of Medicine. Claude Deschamps and the Medical Group Development Fund have supported an additional $1 million to this, and we've just completed a successful search for the new director of this center. So Adam Atherley will be joining us February 1st, 2018. He comes from the Colorado School of Public Health, where he was a professor and a previous department head. His research focuses on health economics and Medicare. So he will be here in short order. I hope you'll take advantage of reaching out to him. He's a very respected health services investigator and will bring a lot of expertise, a lot of opportunity to our research efforts. In terms of cores, we have a very active core directors group that we meet regularly. We've actually completed external reviews of bioinformatics, biostatistics, flow cytometry, and the cell sorting cores. We are very much scrutinizing duplication of effort, services, resources, already making some adjustments in response to that, and continue to look at, kindly from some of our discussions earlier today, Dr. Lorsch, new proposals for cores, how do we sundown cores, and we're looking at ways, invested a lot of effort in trying to help and sustain our cores. One of the first is that at the Dean's office level, we've assumed a bunch of the space charges for the cores under the new budget model that they couldn't sustain. We're looking at co-location and sharing space for members and resources, and we're getting ready to beta test a new integrated business model for some of the cores, where we'll have a shared business manager, we'll share some of the staffing, cost training, scheduling and billing resources, marketing and outreach resources, really all about trying to enhance and sustain our cores. And as I review all the grant proposals that go out of here, I could not be more convinced that our research cores are absolutely critical to our success. In terms of bioinformatics and biostatistics, we again have an active working group. I would say increasingly we're thinking about the cloud in terms of meeting our future computing and storage capabilities. We had budgeted $2.5 million, about $2 million towards new recruitments, and then depending on what's left over, using some of those resources to defray consultation costs, another $500,000 for a joint faculty recruitment in complex systems. The breakthrough here is part of this recruitment process. Julie Dragon has just successfully recruited Adelaide Rhodes as a new bioinformatics faculty member who's just joined us. In terms of research support, one of the high-profile initiatives we had was bringing on some navigators. We recruited the first one this fall, Emily Partington, and keep an eye out. It'll be early in the new year that we roll out testing the navigator role on a sort of a pilot department, if you will. Probably not one too huge, but also not one too small, to see how this works. The navigators are going to be to help investigators with needs, making referrals, a clearinghouse for information, education and training resources. We're also gearing up to try and do some enhanced regulatory and oversight functions, trying to assure that we are in compliance. So hopefully as we move into the new year, you'll begin to hear more about this. We also are looking at other resources to help support major institutional grants, potentially a grant writer and other administrative resources. It's a work in progress. Now this is one of the breakthroughs in terms of support for major institutional grant opportunities. We budgeted $100,000 a year to help support 20 to 40% of PI effort on developing major institutional training grant opportunities. And that salary was at the NIH cap. And for this current year, 2017, we've actually provided salary support to Janet Stein, Beth Patrick, Matt Pointer, and Charlie Urban. There's a relatively simple application process, and the committee review it. But if it's something you're interested in, we have sent out periodic announcements. You just reach out to me. I think this has real potential to help us get major institutional grants out. We also rolled out new targeted thematic pilot research funds. And this was over and above all the other internal grants that we have available. And this was at $100,000 a year. The first year targeted health services research, for sort of obvious reasons, we're trying to roll out that program. So grants went to Brian Sprague and to Prima Menon. But the new one that I'm drafting, it'll come out in the new year, is going to target new methodologies and basic research. So keep an eye out for that. We'll be sending out an email announcement, really probably right at the start of the new year, or even in December. The research incentive program be remiss to say if this wasn't without some controversy when it was developed. And we had a very helpful faculty working group assisting us with this effort. We budgeted $1 million a year over 5 years. You may recall that the incentive was based on a percentage of the total F&A brought in by each qualified faculty member, and that it could be used as a unrestricted discretionary fund or as a bonus payment. The first awards just went out about a month ago, and went to 66 PhDs, 11 MDs, 65% overall took it as a discretionary award to use for research for their grad students, what have you, and 35% as a bonus payment. Now, the critical observation is that we are indeed monitoring the outcomes of how these are going to be used. That was one of the key issues when we received lots of feedback about this effort. So it's a work in progress that we will most certainly revisit. In terms of space, resources, and allocation, we have a very helpful faculty working group here. Sue Ligon and I completed our annual comprehensive tour of all our facilities over the summer. It's a major ordeal. Find closets I didn't even know existed. Always very helpful, though, just a sense of where we are. We, this past year, developed and implemented new laboratory space guidelines that you should have seen. We've disseminated those. We're working now on new office space guidelines. But another new breakthrough I'd like to see some folks take advantage of that we just rolled out is a new shared swing space laboratory facility given E215. And this would be for people, who need some additional lab space over a short period of time, people transitioning in, new investigators, people closing out their program, what have you. And if you are interested in accessing this facility, just contact Elena at this email. But it's a nice, sizable lab that is a shared resource available to our faculty. I'm not going to read all these, but I did want you to understand that we've looked at this carefully and continue to look at it. This is the what came out of the Strategic Research Planning of the Faculty Committee of Basic Science report. You can see there's many things, and there's a big question after the faculty incentive plan, a question after support to the center. What I want you to know is, one, this very much has our attention. Two, we're acting on many of these issues. We can't possibly do them all, but a lot of helpful suggestions, and they're certainly not just putting them to the side. As you've seen already, a lot of these fronts we've made some significant progress on. A lot more work to do. Similarly, this is from the strategic report from the chair committee of basic science, and they recommended that we create a chair's research council that would look at strategic planning, resource use, coordinate faculty recruitment, sharing best practices, enhancing communication. They also thought it would be worth us exploring enhanced central research administrative support for many functions that are currently at the unit level. But number 2 here was deemed the highest priority of all. And we have a subcommittee of the Chair's Research Council that many of you are participating in that is meant to develop research performance metrics and accountability, effectively benchmarks for our faculty engaged in research. And Mark Nelson and Greg Holmes have generously agreed to co-chair that committee. And this will be a minimum of several month undertaking, but very, very important. In terms of research resources and new developments, I don't really need to share with this audience that a lot of our aging infrastructure is falling down before our eyes. This is one of my favorite lab pictures on the right. I'm not sure whose lab is that. Somebody in the rooms? Anyway, repeatedly flooded. So we had that to deal with. So we are moving ahead with an initiative to build a new research building and to renovate the given complex. And you'll be hearing much, much more about this. This is a multi-year undertaking. Just in the past month, Dean Moran gave an informal presentation to the Board of Trustees It wasn't a formal request for support at that point, but they were quite supportive. We're moving ahead with the funding for requests for proposals from architectural teams for this effort. So this is all moving forward, and there will be, as we move into the new year, there will be a ton of opportunity for the faculty and staff to give us feedback and guidance on what some of this will look like as we work with the architectural team. So you'll hear a lot more about this, and I'm not going to go into it all now. We continue to work towards enhancing, especially with the new Health Services Research Center and Steve Leffler's effort in population health with the Health Network, at ways that we can work with electronic medical record and claims databases. Dr. Atherley, coming from Colorado, actually can bring access to some very substantial national Medicare claims databases. One of our biggest breakthroughs of the year is working with Dr. Galbraith here in the audience. We are forging ahead with an electronic IRB. From here on, it's called CLIC, which is really the state-of-the-art electronic IRB. It was a joint undertaking with Waterman, with the provost, with Richard Galbraith, with the medical group, with the medical center, with Claude Duchamp and Eileen Whalen. I think it's just a wonderful example of the kind of collaboration where we can work together to make something really important happen. And this is basically, electronic IRB is really bringing us up to the modern age of clinical research. You also see announcements coming up in short order about the availability of wireless connectivity for some of the laboratories who are now in isolation. And we're also working on research data backup for devices that are not currently connected to the college enterprise storage system, so that is not lost. So a lot of exciting new initiatives there. And then looking ahead here, I'm going to sound like a broken record to some of you, but one of the agendas that we're really pushing is building strong regional consortia focused on research, education, and training. And of course, the big CTR grant is really the first striking example of that. And I view that as just a first step. This is leverage to do much more. So you can see, for example, we have a lot of interest in building a similar initiative around the cancer center. Great opportunities around substance abuse, around opiates, these sorts of things, where we can put ourselves in a much more competitive stature than we could possibly be by ourselves. And again, it's not just about research, it's also about education, training opportunities, and it's not just about clinical research, translational research, it's also mechanistic research. Tremendous opportunity for us here. And I can tell you from our discussions with NIH leadership, this is a very high priority in Washington, just this kind of thing. So we're going to continue to push this. A lot of interest in rural health in northern New England. Aim strengthen our alignment. There's a lot of opportunities where partners are complementary, where we bring different strengths than they may have, for example. Really enhance our competitive stature, and of course we're potentially looking in terms of health services opportunities at a very unique all-payer ACO model for Vermont. And of course it remains that health services, rural health represent our most major domains of alignment and interest with the health network and with our college and everything that relates to it. So strategically, this is a very powerful direction for us. Well, I want to wrap up the state of the college here. This has been a quick overview. First, we continue to look forward to this becoming just a thriving annual event that everyone looks forward to, the celebration of excellence in research. Most certainly don't be shy about forwarding me your suggestions about what we've done wrong. There were so many moving parts in this, I'm quite certain there are little things that will go wrong. I do want to absolutely thank Charlie Urban, Chris Berger, Brittany Willett, Jennifer Nussberg, Joanne McVeigh, Aaron Montgomery. This was a gigantic team effort to pull all this together. Definitely want to thank everyone who made award nominations. And I also want to thank all the faculty reviewers who helped determine the awards. So thank you for that. I would add, in terms of the content of the State of the College address. I'm not going to do questions now because we're short for time, but most certainly I'm happy to visit with anybody about anything you heard today or things you didn't hear today. So, on that note, we're going to jump right into the Excellence in Research Awards. And again, what I want to do with the Trainee Awards is I'm going to announce all the nominees, and then the next slide will be the award recipient. And then what I want to do is have the award recipient and their mentor are present, or someone covering for their mentor are present, to come up. We'll give you an award. You get a quick photo opportunity with Dean Morin and myself. We'll even autograph it later. And we'll try to move right along as expediently as we can. So, first are the Trainee Award nominees for Outstanding Research Publication at the graduate student level, and this includes Devin Champagne, Catherine Chung, Deli Hong, Andrew Lombardo, Jamie Stern, Arvis Sulivari, Emily Tarleton, Joyce Thompson, get this right, Tu Thuy, apologize if I butchered that, and where am I? And Chris Ziegler. And the award winner is Andrew Lombardo and mentor David Warshaw. I should add the citation, obviously, for the winning paper is right there. Okay, and Matt Pointer is going to come up and do the next named award.
Honored to have an award that's been named after the former chair of Dave Warshaw's department, the Norm Alpert Award. And this is given by the Lionheart Charitable Trust and is named for the former chair. This year's award recipient is Jamie Stern in the laboratory of Chris Berger, and her paper, you can see, is up there. And what's really nice about this is, in addition to a plaque that the dean is going to present, come on down, Jamie, is that there's a $300 prize that goes along with it. So we're very thankful for the great work that she's done. And the nomination of Dr. Berger for making it possible.
Get up there. Come here. Somebody's got to dress him. Okay. So the next category of Trainee Awards for Outstanding Research Publication. The medical students nominees are Mustafa Chopin and Catherine Ruth. And the award recipient is Catherine Ruth, mentor Marcus Meyer, and I think you want to come to this? Great. Okay, next award category for outstanding research publication is postdoctoral fellows. Nominees Matthew Alba and John Winters. And the award goes to Matt Alba, mentor Hugh Garavan. I think somebody's covering for Hugh. Jim Hudson. next one is outstanding research publication for residents. The nominee was Kara Landry, who won. Well, don't laugh. We weren't necessarily given them automatically, so it could have been different. Mentor Mary Cushman. I think Chris Holmes is something. Oh, well, come on down. Yep, come on. Congratulations. Now, Claude Deschamps is going to do the UVM Health Network Medical Group Awards.
Good afternoon. I'm delighted to be here and to announce the recipients of several awards that are presented annually by the UVM Health Network Medical Group Faculty Practice. This year, for the first time, we are incorporating this presentation into Larner College of Medicine Research Day in recognition of the high value we place on our academic mission and its importance in informing the clinical care we provide throughout the communities of our network. Our first award is for the Junior Researcher of the Year. We had 2 finalists for the award, Kim Dittus of the UVM Cancer Center and Andrew Solomon of Neurology. And our winner is Kim Dittus. Kim is Assistant Professor of Medicine and Hematology Oncology. Among the highlights of her research career, she developed the first of its kind nationwide oncology rehab program, which she continues to direct and which provide a platform for her research. She has authored 42 peer-reviewed publications to date and has a sustained history of extramural grant support. Help me congratulate Kim. The 2 finalists for the Senior Researcher of the Year are Mort Wasserman of Pediatrics and Beth Kirkpatrick of Infectious Disease. This year's award goes to Beth. Beth is a professor of medicine and founding director of the Vaccine Testing Center. She's widely recognized for her contribution in vaccine development. In vaccine development and testing, she's the author of 57 peer-reviewed publications to date and has an impressive extramural funding record, including from the Gates Foundation. Beth, congratulations. Help me congratulate. Our first $50,000 2-year research grant goes to co-PI Andrew Solomon of Neurology and Richard Watts of Radiology for improving diagnosis of multiple sclerosis through the integration of novel MRI biomarkers. Let me go give you the right slide here. Could you both please come up if you are here? Their proposal would evaluate novel automated imaging techniques to improve early specificity and sensitivity for MS compared to current criteria. They also proposed to develop a computational prediction method using support vector machines that integrate and analyze permutation of tree technique to identify combination that provides the highest specificity and sensitivity to MS diagnosis. Congratulations to both of you. Congratulations. Our second research grant is awarded to PI Sarah Goot of Psychiatry and co-investigator Jim Ojak of Psychiatry and Marge Meyer of Obstetric and Gynecology for the Vermont family-based approach in the perinatal period. Would you all please come forward? This proposal would demonstrate the ability of the Vermont family-based approach to engage women from diverse socio-economic backgrounds in health promotion as indicated by participation in wellness-related activities. It would test the efficacy of the VFBA to improve health outcomes for expecting mothers and also test its impact on parenting outcomes. Congratulations. Our $250,000 grants for innovation for clinical care are new this year and are intended to accelerate the development of innovative approaches within the clinical care continuum, including service, patient engagement, clinical interaction, and broader system or process designs. Our first innovation grant goes to the team of Lee Ann Shofredi, Erica Gibson of Pediatrics, Abigail Crocker of Mathematics and Statistics, Andrea Vivlenti of Psychiatry, and Daniel Wolfson of Emergency Medicine. Could you please come forward? Their proposal is titled Developing a Multidisciplinary Model to Improve Care of Emerging Adult with Alcohol and Substance Abuse. This proposal in the long term would implement and evaluate an interdisciplinary intervention to improve identification and treatment of alcohol and substance abuse in adolescent and emerging adults. This project will specifically identify the characteristics of patients most likely to benefit from screening, brief intervention, and referral to treatment, and determine the current perceptions and barriers to implementation in the ED and inpatient settings. Please join me in congratulating. Finally, our second and last innovation award goes to Abiv Ambai, Pam Gibson, and Douglas Stagis of Pathology and Laboratory Medicine for their proposal, Determination of Diagnostic Concordance between Whole Slide Imaging and Conventional Light Microscopy for Select Routine Surgical Pathology Applications in the University of Vermont Health Network. Would you please come forward? They're already here. This team will evaluate the diagnostic equivalence between whole slide imaging and conventional light microscopy for surgical pathology diagnosis. They hope to demonstrate that digital diagnosis of surgical pathology cases can be performed by network pathologists with different level of experience, and that the digital diagnosis of surgical pathology cases can be performed by pathologists in community as well as academic settings.
Thank you very much. Congratulations to all the Health Network Medical Group recipients. We're going to jump back in now to the Dean's Excellence Awards for faculty. And the first one is the Research Mentorship Award. The nominees were Yvonne Johnson-Henniger, Renee Stapleton, and Richard Watts. And the award recipient, Yvonne Johnson-Henniger. Hold on. That's great. So let me say a few words before we do our photo shoot here. She was nominated by Deborah Leonard. Deborah, you can come down and join the picture as well. We'll take the, well, you can take a selfie. So Yvonne is professor and vice chair for research in the Department of Pathology and Laboratory Medicine. Her mentees include 5 high school students, 16 undergraduate, 16 PhD students, and 12 postdoctoral fellows. Her mentees have won a great variety of prestigious awards and even been funded by NIH R1s. And 7 of her mentees currently hold faculty appointments in academic institutions. Now we can jump to the photo. Okay, next faculty award is the Rising Star Assistant Professor Award. Nominees are Vikas Anathi, Matthew Kinsey, Joshua Nickerson, Michael Privis, and Benedict Erdos. And the award recipient is Vikas Anathi. So Vikas was nominated by Deborah Leonard, so we'll get her in the picture again. He's assistant professor of pathology and laboratory medicine, and his research is focused on endoplasmic reticulum stress in allergic asthma. He's been funded from a variety of foundations and also has received an NIH R1. He's published 28 peer-reviewed research papers. Okay, next category is mid-career associate professor category. Nominees were Chris Houston, Sally Hershon, and Alan Howe. The award recipient is Chris Houston, nominated by Charlie Irvin. So Chris is Associate Professor of Medicine and Infectious Disease Medicine. His research focus has been cryptosporidium drug development and testing. Has a strong funding record by NIH, and the Gates Foundation has published 31 peer-reviewed papers. We really couldn't be doing this any better. Our target was 5 o'clock, and we're a few minutes short. So very impressive. Everybody's staying right on cue here. So the last of our awards is the Research Laureate Professor Award. And remember, this is the one that includes giving an oral presentation in the spring. Really our preeminent recognition for a senior investigator here in the college. And I would add up front that we have a lot of very qualified individuals, and it's going to take us at least several years for them all to win. And I think and seriously, there are a number of folks here who are all right at the very top. So I don't want anyone to be dismayed if they didn't get it this year, because you will in relatively short order. I mean, it's really a testament to the college that we have so many really productive, exceptional people, and it's going to take us a little while. So what we are doing is we're rolling over previous nominees with their permission, and they'll send in updated materials and CV. So included in this pool were Bruce Bainin, Jason Bates, Sylvie Dublier, Chris Franklin, Steve Higgins, Gary Stein, Roger Soll, Don Weaver, Marie Wood, and Jane Leon. And the winner was Gary Stein, who was nominated originally by Fran Koch. So, waiting for Fran to come down. Gary is director of our Cancer Center, professor and chair of biochemistry and professor of surgery. He was just named the Arthur Jason Perelman, MD 52 professor in cancer research. And his research is focused on genetic and epigenetic regulation of cell proliferation and differentiation, with an emphasis on cancer. He's published more than 900 research papers, had continuous funding from NIH, including R1's program project grants and the new CTR grant, and he's a fellow at the American Academy of Science. So congratulations, Gary. So that was the awards for the day. I hope you all concur. Really a very exceptional group of people. And really all the nominees are to be congratulated. I think that this is a really fun, special event for the college. So we're going to move on really to the keynote presentation of the day. We kept the very best for the last. And John Larsch, who's director of the National Institute of General Medical Sciences, is going to give a talk entitled "The Foundation on Which Advances in Medicine Are Built, Basic Research." And I do want to make a call out. They're probably going to be on about 5 minutes. Are they already on, you think, our colleagues from Maine? Anyway, we are actually exactly 5 minutes. So we'll have to stall for a few minutes. Well, actually, we'll have to stall anyway because this monitor's off and we need to get on for John. Anyway, we are streaming Dr. Larsch's presentation to our CTR colleagues at the Maine Research Institute in Portland. And again, this is just a way of highlighting the collaboration that's developed. We actually did the same thing with the Stetson lecture in September as well. So we're sharing a lot of material back and forth with our colleagues in Maine. And I'll turn it over. I guess we can go ahead and can we go ahead and do the introduction, I think? Even though we got 4 minutes? Might as well. Go for it.
Let's talk about all your papers. A little payback for all the shots you've taken at me today, but that's okay. Gordon and I were talking about who we'd invite, and I thought that it would be terrific if John would come and visit us. And I was actually really shocked and pleasantly surprised when he said yes. because any of you that know about the folks at NIH have limited travel funds, and they have to be very selective about where they go. So we're really honored and pleased to have John here. The main reason that I wanted to invite John was that last year, Chris Berger and I went to a meeting at NIGMS. And John gave a remarkable talk at the beginning about transforming graduate student education that really resonated with me. And I thought that what we're doing with medical students here at the college could be extended to graduate student education. We could really make an impact. Now, John got his BA in chemistry at Swarthmore. I'm surprised you don't have one of those pocket protectors. Then he went and worked at Harvard, did his PhD, and he did his postdoc at Stanford. And then he went to Johns Hopkins, where he rose through the ranks. He has multiple papers. CNS is a word I learned down at NIGMS. It isn't for central nervous system. It's cell, nature, and science. Chapters, patents. Well, what I didn't know about him is that he'd won 6 teaching awards at Johns Hopkins. And in his CV is this really interesting paper that is a real interesting read. And I heard a lot about his views about education today, and came out in many of our meetings. And we've been promoting educational scholarship. How about a paper in Cell on teaching graduate students? That's really quite remarkable. And it was a seminal paper that had to go through peer review, et cetera. And then in 2013, he became the director of NIGMS, which was a big job. And and that's how I got to know him, through the IDEA program. And he's been a staunch supporter of that program, which is really important for those of us in the IDEA states. So without further ado, John, thanks for coming.
Open it for me. That's real service. There we go. Put it on there, right there. There we go. Thank you very much. How many deans does it take to? That's good. Thank you. My daughter and I have a question, which is, if the 2-letter abbreviation for Vermont is VT, why is this place UVM?
University of the Green Mountains, Veritas Mountains. Flat.
Vermont. Yeah. Got it, okay. I'll take that one back home. Well, thank you very much for inviting me to speak here, and Charlie for putting up with me today. It's a real pleasure to come and speak with all of you. I've had really great talks today. I wanted to talk a little bit about basic science, which is obviously important in medicine, but I think isn't always appreciated by everyone for just how important it is in advancing medicine and eventual clinical practice. So let me start, though, by orienting you a little bit to NIGMS and its mission. So the Institute focuses on 2 main things, which is, first of all, basic science. So we support basic science with the premise that increasing our understanding of biological processes will eventually form the foundation that leads to advances in disease diagnosis, treatment, and prevention. We do have a few clinical areas that we're responsible for, particularly those that cross multi-organ systems: sepsis, anesthesiology, trauma, burn, and perioperative wound healing. So those are some clinical areas. And then we're also known as the Training Institute at NIH because we support the biggest training budget by far of any institute. Almost half of the pre-doctoral training slots that NIH as a whole gives are given by NIGMS. So we have a mission to promote the training of the next generation of scientists, to enhance the diversity of the research enterprise, and to build the capacity across the nation to conduct cutting-edge biomedical research, which is where the IDEA program sits in the institute. And so what I want to do again today is to tell you about why we have this focus on basic science at NIH, the National Institutes of Health. 2 years ago, we produced a strategic plan for the next 5 years. And the first goal of this strategic plan is to maximize our investments in investigator-initiated biomedical research to drive fundamental scientific discoveries and advance the understanding of human health and disease. Underneath that goal are two strategic objectives, and they're really what I'm going to focus on today. Invest in and sustain a broad and diverse portfolio of meritorious research, so broad and diverse being the key words there. And then second, to promote the ability of investigators to pursue new research directions, novel scientific insights, and innovative ideas. So I want to kind of delve into why we made this the cornerstone, and these concepts the cornerstone of our strategic plan. And I'll start just by talking for a second about the Nobel Prizes. So you may have seen the Nobel Prizes in chemistry and medicine were awarded last month. And of those 6 Nobel Prizes, 4 of them, all 3 in medicine or physiology and 1 in the chemistry side, were supported by NIGMS for most of their careers. And the work that was cited by the Nobel Commission was supported by NIGMS. And since 1962, that brings us to 87 Nobel Prizes supported by the Institute, which is well over half of the 153 that were supported by NIH. And we're just 1 out of 27 institutes and centers. So just right there, I think you'll say that the focus we have on basic research, and on investigator-initiated research, and on a broad and diverse portfolio is, at least by the metric of Nobel Prizes, successful. And I want to delve into this a little bit more. So in 2017, the committee, when they announced the prizes, had a press conference, and this is a picture of that press conference. And the guy in the middle there is the Secretary General of the Swedish Academy of Sciences. And during the press conferences, a reporter asked a question, which I thought was really quite interesting. And she noted that at that point, 3 of the Nobels had been awarded: chemistry, physiology or medicine, and physics. And of those 9 prizes, 7 went to Americans. And so she asked, what is it about American science that is so successful in terms of leading to this transformative Nobel Prize winning work? And I thought that Professor Hansen made a really, I think, quite brilliant statement in response to this question. He said, the United States has allowed scientists to perform fundamental research, also known as basic research, to focus on important questions in science, not forcing them to immediate applications, not controlling them in a political way. And that freedom, combined, of course, with very good resources, have been very helpful to the United States. Okay? So again, focus on basic research, focus on investigator-initiated research, not directing it from above. And somehow he attributes this to the success the U.S. has had in producing transformative Nobel Prize-winning research. And so what I want to do today is start by telling you 2 stories that I think illustrate what Professor Hansen was talking about there. One of them is an old story, and one of them is an ongoing story. And then I'll try to interpret these stories a little bit for you and put them in context. So the first story starts a long time ago. This is a historic one, 1961 at Michigan State. And this is the hero of the story, Barnett, also known as Barney Rosenberg. And he was a biophysicist, newly arrived at Michigan State. And he was interested in how cells divide. I talked to a number of students this morning and postdocs about their work in cell division. So here's your cell division story for you. So in particular, he was interested in how DNA is replicated and then pulled apart as the 2 daughter cells spin off from the one cell. And he noticed something he thought was intriguing. So on the left here is something that's probably familiar to all of you who took middle school science. If you take iron filings, you put them down on a piece of paper and you put a magnet under them, they align themselves really beautifully along the magnetic field. And that's a picture of, the magnetic field aligning iron filings. And he noticed that that pattern looked surprisingly like the pattern of chromosomes, the DNA in the chromosomes during cell division. So at the bottom on the right is a picture from a micrograph of the chromosomes lining up as the cells are dividing. And I think you can see that looks surprisingly like that iron filing pattern. And on the top is an actual fluorescence micrograph of the chromosomes in purple lining up, and then the microtubules around them. So he thought, well, this looks surprisingly similar. Maybe there is some relationship between these two things. And that wasn't completely crazy because, as you probably all know, DNA is a very charged molecule, so it has an electromagnetic field. And maybe somehow that electromagnetic field was being used to pull these chromosomes apart in another field. So he decided to test this, and he did an experiment to look at this. And what he did was he grew a simple model organism, E. coli, in electric fields. And you should actually go, if you're interested in the history of science at all, and read this paper. It was published in Nature in 1965. And it starts with this beautifully understated line at the top. And in an investigation of the possible effects of an electric field on growth processes in bacteria, we have discovered a new and interesting effect. So that ranks up there with Alexander Fleming's first paper on penicillin, which said something similar about he made an interesting observation which might have some relevance to bacterial diseases. Another great paper that you should read if you hadn't. But his experiment was this. He took platinum mesh electrodes, like the one shown there, one on each side of a tank in which bacteria were growing, E. coli, and he put electric field across it. And he says in the paper, platinum was chosen for the electrode material because of its well-known chemical inertness. And 1,000 coulombs per second was chosen to eliminate electrolysis effects and electrode polarization. That was the basics of this experiment. Then this great line, as we will show, both are mistaken ideas which led via serendipity to the effects described in this communication. Right? So this is the control, basically saying that's why we chose these things, because they're inert. It turns out wrong. Okay? So what does he see? He's growing the bacteria in this tank with these electrodes on either side. And he sees something kind of remarkable, which is normally, as you know, E. coli are these little rod-shaped bacteria, like shown on the left. But when he put the electric field across them and grew them for a while, they turned into these giant strings, basically. And because he was an expert in studying cell division, he didn't just say, that's weird. He recognized this as a defect in the process. So the bacteria were still growing, but they couldn't divide anymore, and so they just get longer and longer and longer. Now, he could have stopped there, as many people might have, and said, my hypothesis is correct, right? We're in an electric field, and they turn long, and so electric field must have something to do with cell division, with pulling the chromosomes apart. But Barney Rosenberg was actually an excellent scientist, and he didn't stop there. He didn't just assume, based on this one observation, that he was right. He started to do control experiments. And one of the control experiments he did was to say, well, although I chose platinum because of its well-known chemical inertness, maybe we should test this. And so he changed the electrode material. He used copper instead of platinum. And guess what? He didn't see the effect anymore. It looked like the bacteria on the left, just perfectly normal. So it's not the electric field, it's the platinum. So this then led, after a series of additional experiments, to the discovery that what was causing this was not the electric field at all. It was that the electric field was causing this platinum to turn into a new form of platinum called cisplatin. Okay? And it was the cisplatin that was interfering with the bacterial cell division for very interesting reasons. And that was leading to the formation of these long filamentous bacterial forms. Now, he said that the isolation of this molecule led him to what he said was a purely intuitive jump, although, as you'll see, it was a jump he made because, again, of his expertise in understanding the basic science of cell division. And that intuitive jump was he knew that other molecules that produced similar defects in bacterial cell division had some anti-cancer properties. And so he wondered, maybe this molecule will have some anti-cancer properties. And so he partnered with a woman, Vivian Mansour, down at the bottom, who knew how to do the experiments in mice to test whether this compound had any anti-cancer properties. So they would create a sarcoma in a mouse, and then they would test it to see whether cisplatin reduced that tumor at all. And one of the things I'll note, if you can, this is a bad image because it's the original figure, but if you see they have a number next to the mice, which shows how many mice were in each group. And I swear those are the candles that you put on top of a birthday cake. I mean, look at them. They're crazy, right? So anyway, so I just note that too for you. But the experiment's really quite impressive. So in the control experiment, you can see it, the mice you can see grow very large tumors, and by 3 weeks, they're dead, all of them. However, a single treatment of this cisplatin in the same experiment in the non-control group, the mice live not just past the 3-week mark, but to 36 days, and their tumors are dramatically shrunk. One injection of this material. So that was impressive. Based on these positive animal studies, he was able to get clinical trials in humans eventually set up, and this led to eventually the approval of cisplatin in 1978 by the FDA for the treatment of testicular, ovarian, and bladder cancers. Note, though, 1961 is where the story started, FDA approval 1978, so we're nearly 20 years later, right? Okay, so that's one important point, the length of time this took. This is something I got off the NCI's website. In particular, cisplatin's success as a chemotherapy drug against testicular cancer is phenomenal. This is the NCI. When used in combination with other chemotherapy drugs, its cure rate is more than 90%. Okay, truly transformative. It's not just been used against those cancers, but a variety of others that you can see here. And an expert at the NCI said, the patients cured by these regimens and those that have benefited from this therapy number in the millions. It would be frightening to imagine the current status of cancer treatment without this essential drug. So from a purely curiosity-driven experiment to look at the effect of electric fields on cell division in a model organism, the humble E. coli, millions of lives have been saved. Right? Phenomenal, essential drug. So that's the first story. The second one is an ongoing one. It's just something that I'm very excited about, and maybe I can give you a frame of reference for current basic science that could be transformative eventually. So here are 4 animals, 4 organisms. One's a fish called the beacher. It's a fish that, as you can see, can use its flippers, its fins, to actually walk around, and it can come up on the land and walk. And some people, evolutionary biologists, think this may have been related to the original fish that came out of the water and eventually became the forerunners of us, right? Developed feet and were able to walk around. On the right is the axolotl, which is the Mexican salamander. Below that, its cousin, the newt, and on the left, another fish, the zebrafish. And what all these animals have in common is the ability to regenerate their limbs and their organs if severely damaged, like amputated. So for example, if you were to cut off the leg of a salamander, or a fish comes along and bites off the leg of a salamander, what will happen at first is there'll be wound healing, as you see on the left at the top. But unlike a human, where if we lose a limb and we get wound healing and get a stump, that's the end. In salamander, over the course of 40 days, that stump will completely regrow into a new limb, good as new. Think about how remarkable that is, right? And lose its entire leg and then just regrow it. Zebrafish can, although they don't have legs, but they can do something similar. So you can amputate the tail fin of a zebrafish, and over the course of about 20 days, it will regrow a completely new tail fin, good as new. So that's remarkable. There are even more remarkable animals, like the planaria, right, which you can cut into 3 pieces And each piece will completely grow a new planaria, right? So you can cut off its head, cut off its tail, the middle section grows a new planaria, the tail grows a new planaria, and the head grows a new planaria. This is truly incredible. So not only can the limbs be regenerated in some of these animals, but their organs can be. So imagine, though, the limb regeneration part. If we could figure out how to make us regrow a limb, say a soldier in battle loses a limb, someone in an accident loses a limb, we could develop some kind of a drug or a therapy that would allow the processes to take hold again and regrow that limb. That's like science fiction, but there are actually more immediate applications to think about now in terms of the organ regeneration. So in zebrafish, or in a neonatal but not an adult mouse, pretty severe heart damage can take place. In fact, in a zebrafish, you can cut off a significant fraction of the heart, and the fish will actually regrow that heart as good as new. Same with a neonatal mouse. Of course, in a human, you know that's not true. And in a myocardial infarction, when there's damage to the heart, what happens instead of regrowth of a perfectly new heart is scarring. Scar tissue forms, and that scar tissue doesn't have the same properties as the original heart, and that can lead to further heart complications and eventual heart failure. So again, imagine if you could find some way to promote the regeneration of our heart tissue after a heart attack instead of the formation of scar tissue. So that all begs the question, if these animals can regenerate their organs, can regenerate whole limbs, if amputated or lost, why can't we? It turns out to be a better question than you might have even imagined, because we share all the same biochemical and cellular pathways with the salamander and the zebrafish that they have. It's not that they have some special pathways that we don't. They seem to have all the same machinery, all the same signaling molecules. We just don't turn them on in the same way after damage that they do. So we form scar tissue, our nerves don't grow in the right way, our blood vessels don't grow. There are differences apparently in how our immune system reacts to this damage from theirs. And that leads to our being unable to repair these tissues and their being able to completely regenerate them. So maybe if we understood more about how these pathways worked, we could actually turn them back on in us at the right times and repair damaged hearts or even regrow lost limbs. That sounds like science fiction, but given that we have all the same molecular machinery, all the same cellular machinery, it seems like it should be possible. So what's the problem? Well, the problem is that despite a lot of progress, we still don't know how all of this works. And it's also very complicated, is the second problem. So here's just one picture, and this is just a simple cartoon of some of what we know about how heart regeneration and development works, some of the molecular underpinnings. And you can see there's at least 3 signaling pathways involved, a lot of changes in transcription. You're not supposed to take any of this in, but it just goes to show we know a lot, it's very complicated, but we don't know nearly enough, okay? So one of the points, of course, is that in order for us to be able to understand what goes wrong, or why in this case we can't do something that a salamander can do, we need to know more. We need to know more basic science. And eventually the hope is that we'll then be able to figure out how to intervene and, in this case, turn those pathways back on at the right time. So what are some of the principles then from these 2 stories? So the first one is that old Pasteur saying that chance favors only the prepared mind, right? And that was clearly evident in the story about cisplatin. You could say, oh, it was just serendipity, so should we all just be doing random experiments, and it doesn't really matter if you're an expert or not. But that was not the case at all in that experiment, nor was it the case with Alexander Fleming, which is a whole other lecture I could give. The reason Rosenberg made the discovery he did was because he was an excellent scientist and he knew a lot about the processes he was studying. He recognized what he saw as a defect in cell division. He knew that other compounds with that same property had proven useful in cancer. He had the prepared mind, and he was an excellent scientist. I think it's also very critically important to recognize that breakthroughs, tend to think of these eureka moments, actually emerge on a complex foundation of fundamental information knowledge. It's accumulated by many researchers over many years, and I'll show you actually a demonstration of that in a second. But it's not that someone was sitting in a lab and just something popped up and there's the answer. That emerged on a complex foundation of other people's experiments, the investigators' experiments, and it's very difficult to know which piece, which strand was the most important. Similarly, breakthroughs come from unexpected and surprising places, right? So it's very difficult for me or any funding agency to say in advance which of you is going to be the one that makes the final key discovery that leads to the medical breakthrough. And also, as I said, to understand which strands of other information form the foundation on which your breakthrough emerges. Organisms that are distant from humans play a key role in providing insights and understanding that lead to advances in medicine technology. The humble fruit fly was the subject of this year's prize once again in physiology or medicine for our understanding of circadian rhythms, which have all kinds of implications for medicine. So thinking that you're going to advance medicine only by studying humans, I think, has been proven wrong time and time again by the history of science. And finally, and this is kind of bringing all of this together, one of our jobs is, or a fundamental job is to act as investors of the taxpayer money. So Congress entrusts us with a lot of funding, that is taxpayer funds, and asks us to invest it in the most efficient, the most effective way possible in biomedical research. And just as investors in the stock market know that the best strategy is to have a broad and diverse portfolio because it maximizes the upside potential and spreads the risk, the same is true in investing in biomedical research for the reasons I've told you, right? If we aggregated all of our funding in a small number of people, we're almost certainly going to miss the big payoffs because we don't know in advance where they're going to come from. And even more in the sciences, because those payoffs are riding on the foundation that was built by many researchers before them and wouldn't emerge otherwise, having a broad foundation being developed is critical for those occasional big payoffs to emerge. I could prove this to you to some extent because there have been people who have been studying it. There's a beautiful paper that was done by UCSF and the Gladstone Institute a couple of years ago where they used big data analytics to track all of the foundational research that led to 2 big medical breakthroughs. And actually, NIH has now adapted this and has done it in a number of other cases that sees the same thing. So at the very top, that little point on each side, that's a newly approved drug by the FDA. In the case on the left, it's a melanoma drug, first in class, really transformative. On the right, it's a cystic fibrosis drug, also first in class, totally transformative for a certain fraction of cystic fibrosis patients. The cluster below those are the clinical trials that underlay the FDA approval of those 2 drugs. And then beneath that is all the work that led to those clinical trials taking place. So in the middle in green and yellow are the papers that were cited to put those clinical trials forward. The yellow ones are the particularly important ones. The green are also as part of the network. On the left in purple, those are the researchers who contributed to those papers. And on the right are the institutions that they came from. Key points here are there are literally thousands of researchers in both of these cases who did seminal work that was needed to get to those clinical trials at thousands of different institutions over decades. Okay? In the case of the left, the melanoma drug, over 100 years it took to get there, according to this analysis. Nearly 60 years for the cystic fibrosis drug. Okay? So that really shows that science, these great medical breakthroughs, don't happen as single eureka moments. Decades of work by literally thousands of people at thousands of institutions is what's required. That's a very important message, I think, both when you're trying to explain how science works and when you're thinking about how to invest the taxpayers' money. You can also see this in a more recent paper that looked at patents and also FDA-approved drugs in general. And what it turns out this was a work done by Danielle Lee and colleagues at MIT, and what they saw was that 30%, about a third of all NIH grants are cited in at least 1 patent. So they looked over time, and after about 10 years, it kind of plateaus out, but 30% or so of all NIH grants, which is really remarkable if you think about how many NIH grants there have been in that period of time. And a third of them end up being cited in at least one patent. And it doesn't matter, it turns out, whether they're disease targeted or not disease targeted. About the same fraction end up being cited in a patent. So the basic science, almost as frequently as something that was actually targeted, directed at a specific disease, it ends up in patents. Of course, the patents lead to FDA-approved products at a lower rate, only about 5%. But that's still remarkable if you think about it. 5% of NIH grants are cited by the work that leads to an FDA-approved drug or other therapy or test. Right? I think that's pretty remarkable. All right, so going back then to this part of our strategic plan, this is why we're so focused on investigator-initiated research, because we don't know where the breakthrough is going to come from. The great ideas come from the Barnett Rosenbergs studying the thing that they find to be curious and heading down some path and making a breakthrough eventually. The broad and diverse portfolio is critical because, as I said, that's how we're going to maximize the chances of funding the person who makes the breakthrough and also create the foundation on which the breakthroughs will emerge. And again, the ability to pursue the new research directions and insights and innovative ideas is the freedom to explore, like Rosenberg did, or the people studying salamanders. Right? Not obviously applicable to medicine, and yet that may be where the next transformative drug comes from. So these are the principles that we really hold central to the Institute, but there are some challenges that we faced. And one of those challenges has to do with the distribution of funding, something I've been thinking about for a while. Many of you have seen these graphs before, but this is a plot that splits investigators funded by the NIH into deciles, with the best funded on the left and the least well funded on the right. And the key take-home message is that the funding is highly skewed, such that 10% of NIH-funded investigators are getting 40% of the NIH funds, and 20% are getting almost 60%. So it's very skewed, and that's a challenge if what we want to do is to have a broad and diverse portfolio, as I told you, for the reasons I told you. So for these reasons and for the reasons I told you before, we've been experimenting with different funding mechanisms that we hope will try to rebalance things and get to a more productive and efficient state. So I just want to quickly tell you about one in particular, which is the Maximizing Investigators Research Award program, or MIRA, that we started about 3 years ago. In a nutshell, the idea is to give a single grant to a PI to support his or her research program, to provide support for that program. Once they have that grant, that's the funding that NIGMS gives them. And that's in contrast to the current model, which is one in which they break their work up into multiple projects and they can get multiple grants to fund those multiple projects. And we hope that there'll be a number of benefits that come out of this related to what I've been telling you. The first is to increase the funding, increase the stability of funding for investigators. And we reason that if we can increase the stability of funding, we'll improve their willingness to take on ambitious projects and approach them creatively, because they won't be worrying as much about whether they're going to still be funded in a few days or a year, right? That worry about funding, we think, is a dampening effect on ambitious science. We also want to increase the flexibility for investigators to follow important new research directions as they arise during the course of their work. We don't want to lock them in into saying, okay, tell us exactly what you're going to do over the next 5 years, because as you saw from Rosenberg's story, it ain't how science works, right? You have no idea what's going to happen next week, any of you who are in the lab, let alone what's going to happen 5 years from now. So we want to give people the flexibility to follow those strange observations like Rosenberg had. We want to improve the distribution of funding for the reasons I told you, that if we aggregate too much funding in a small number of individuals, we're actually decreasing the chances for the taxpayers of getting breakthroughs. That's our job, is to improve the chances for getting breakthroughs. We also want to reduce the time both spent writing grants by researchers and reviewing grants, because those are both things that are taking away from them actually doing the research that is going to advance science and medicine, and also take time away from mentoring their trainees, which is also going to advance science and medicine. So those are the overarching goals. The way we achieve that, again, is to give a single research grant per PI, and we're using a new mechanism called the R35. The goal is to make them on average bigger than a current NIGMS R01, and they are longer than a current NIGMS R01, so instead of being 4 years, they're 5 years. For the established investigators, the EIs, the direct costs can range anywhere from $10, if you want, to a cap, a hard cap of $750,000. Very few people get anywhere near that cap, but we do actually have a limit, unlike an R01. They're not tied to specific aims for the reasons I told you. We want to give people flexibility. And in fact, there are no specific aims at all. It's a short 6-page application for the research strategy. And instead of having the specific aims with the details of all your experiments and all the controls, what we do is ask you to broadly delineate what it is you're working on, or you think you're going to be working on, why those questions are important, why you're the right person to answer those questions. The de-emphasis on the details of the experiment. So the review is based on the track record of the investigator and the overall research ideas. Again, why are these the important questions that you think need to be answered, and why are you the right person you think to answer those questions? There's also a consideration of service and contributions to the workforce development in the review of these applications. So if you've done something important for building diversity or helping the scientific community in some way, that can be factored in as well. We want to incentivize those things. Now, I said that stability is important here. The extra year helps with stability. But more than that, we want to change the funding model from a digital one to what we're calling an analog one. So currently, you put in your R01 renewal application. Study section says, yeah, you did good work, but you're not the top of the pile. You're just probably not going to get funded, right? And that's a huge inefficiency in the system if we have meritorious investigators with functioning labs doing important work who are going between funded and unfunded overnight with relative frequency, right? Instead, what we'd like to be able to do in those situations is to say, okay, we're not going to be able to give you the full amount you had before because the study section maybe didn't think you were quite at that level. But we're not going to cut you off. We're going to ramp you down to a new level, which is going to require shrinking your lab a little bit, and then fund you at that level for the next 5 years. By the same token, if someone does really well, we can ramp them up. So we're going to have this dynamic flexibility to not just say yes or no, but to change budgets based on the review. Now, there's an established investigator version of this, and I'm going to tell you about both these in a second in more detail. But we also started an early stage investigators version, which I thought was very important to bring people directly into this system. But that created a problem because if you're reviewing based on track record, how the heck are you going to compare someone just starting her lab to someone who's in the National Academy and has a lab for 30 years or more? So we didn't do that. We separated them. And so we're completely separating the review of the early stage investigators from the established investigators. They're separate review panels, and they actually have separate review criteria for those two groups. So we're comparing apples to apples and oranges to oranges, which I think is a pretty significant advance, actually, in how we deal with bringing new people into the system. Okay, so we started out as a pilot. Now we're expanding it. So now, for the established investigator MIRA, anyone who has an NIGMS R01 can apply when their R01's up for renewal to try to convert it to a MIRA. There are two flavors of this, right? There's going to be a flavor of people who have a lot of money, or in that 10% that has 40%, and everybody else. And so we're going to treat those two groups a little differently. So in the first group, for well-funded investigators, people who have over $400,000 in NIGMS direct costs, what we're telling them up front is you're going to get the benefits of a MIRA if you get it, but it's going to be in exchange for having a little bit less money. And that's what we've done in the first two rounds, which really shocked the system initially. I think people didn't believe that we were serious. And we ended up, on average, reducing those people by about 12% relative to their 3 to 5 year average funding history. So to us, maybe 12% doesn't sound like a lot. To the people who had it, boy, it sure seemed like a lot based on how much some of them yelled. But what we're doing with that money is funding other people. So we want to fund additional investigators, whether they're early stage investigators or mid-career investigators who otherwise would have to close their labs. And we're also working to increase the budget for the average person. So most people who have one R01 are getting $210,000, $220,000. We want to increase that at least a little bit to try to bring back some of the losses to inflation that have taken place over the last couple of decades. So to that end, if the investigator currently has a single modular R01 for, say, $210,000, our goal is to increase that to $250,000 as a median. Okay, so we want to bump people up who are trying to survive with around $200,000. So far, we've made 231 awards. We have another competition happening right now. The first two rounds of the established investigator we reviewed in-house at NIGMS. That was really the pilot. We're now moving those to the Center for Scientific Review, CSR, because it's going to be a bigger load. Then to the early stage investigators, we've had 2 rounds of those so far over the last 2 fiscal years. The success rate's about 29%, which compares pretty favorably with the early stage investigator R01 success rate. So it's pretty good. 192 awards made to date. And for this group, we have given them, if they asked for it, $250,000. That's the maximum they can ask for. And if they asked for it, we gave it to them with no cuts. Okay? That compares to the $198,000 that they would have gotten if they had applied for an R01 as an ESI from NIGMS. So they're getting about $50,000 more than they would have, although they can't apply for another NIGMS research grant. But remember, if they do spectacularly well when they come in for renewal, we can increase their budgets. Okay. And those were reviewed by CSR originally, but now we're moving those in-house. So we're going to be running all of our own reviews for the early stage investigators coming into NIGMS. Okay, now I just want to end talking about communication a little bit. So Charlie's put all these buttons on. You want me to put all these buttons on, Charlie? Is that what I'm supposed to do? There's like 10 of them up here, but ask me about my research. So that's very topical, because I wanted to end by talking a little bit about science communication, which is something we've been interested in and is a particular challenge for basic science. And if you think back on the stories we just talked about and conclusions we came up with based on those stories, you can see some of the challenges. So first of all, the timeline between doing basic research and an eventual breakthrough in clinical application is very long. In that Gladstone study, one of those drugs was 104 years, the other was nearly 60 years. Right? So the work that any of us are doing basic science right now is probably not going to lead to a direct clinical application for some decades. Okay, so that's problem number one with communicating about it. The other problem is we tend to think about papers as the unit of measure of science, because that's kind of the currency of science, right? And that kind of translates then into a unit of communication. And yet, a paper in basic research, and also in clinical research, is rarely the answer, right? In all of our papers, there's probably at least one thing that's not true. Not that we made it up or anything like that, which is wrong, right? That's how science works. It's the accumulation of papers and science and knowledge over some time that leads to an understanding that eventually leads to some breakthrough. Again, decades. But a paper in and of itself is inherently usually an incremental advance. Not to be pejorative, but that's just the way science works. And it's often sort of 2 steps forward, 1 step back, really. And yet we tend to think about it as every paper is a breakthrough. Right? That's how we tend to discuss these things. And as I said, the work of many researchers over many years is really what leads to these breakthroughs, with this foundation building up to the eventual breakthrough. But it's very hard, even in retrospect, to find a linear path from a paper to the breakthrough. And it took this big data approach to map all of it back, and even then you can't really say which strand is the one that was critical. But this all leads to this problem that's very tempting for us to oversell the basic research results. What we want to say is, when you ask me about my research, I'm curing cancer, right? Or I'm curing diabetes. That's what we want to say, and that may be the long-term hope, which is fair, and we should be talking about. But our individual paper is unlikely to have cured cancer or to have cured diabetes. And I say this because this is something that I found very troubling when I first got to NIGMS. Our whole communication strategy when I first got there was based on press releases that came out of universities. Every press release that mentioned an NIGMS-funded study that came out of a university or other organization came across my desk. I would get several a day. And I was amazed by how many times cancer, diabetes, and Alzheimer's are cured in 1 week. And so this is kind of where this came from, this concern. And so we actually talked with FASEB, the Federated American Societies of Experimental Biology, which represents, I think at this point, 130,000 researchers and 32 different professional societies, about this problem. And jointly, we organized and housed and hosted a workshop on responsible communication of basic biomedical research. And we had science journalists there, we had scientists there who were interested in communication, we had public information officers from industry and from universities, researchers who study communication, and other interested stakeholders. Erica Check-Hayden gave the keynote address. She's a well-known science journalist, used to work for Nature, now still does freelance work, but is also the director of the Santa Cruz Science Writing Program. And a number of principles and ideas came out of this discussion, which I just thought I would share with you. The first is that instead of writing about individual papers, which have the problems I tried to outline a minute ago, it's probably a better idea for us to be talking and writing about the arc of a field, right? Where has this field come from? Why are the questions important? Where is it going? What are some of the growing understanding that we've got? Rather than this one paper told us the answer and that's going to cure this disease. So writing about the arc of a field or talking about the arc of a field is a much safer and I think more reasonable approach to it. Writing about the people doing the work is also something that was discussed quite a bit. People want to hear about other people. They want to hear about where you came from, why you study the thing you study, why does it drive you? And in talking about the people, you can talk about the science too, but it's done in a way that's much more driven by the questions than it is by eureka discovery. I think that's also a much more safe and also engaging way to talk about science. They talked a lot about embracing and helping others understand the uncertainty inherent in science. We try to tend when we talk or write about it, when someone asks you about your research, to say, I proved that this is the case. And of course, you didn't, right? And you may be wrong. So I think getting people to understand that there is uncertainty, and that's part of the beauty of the process of science. Talk about the process and the questions and the fact that we're not sure yet. We're starting to move in this direction is really important for the public to understand. Because what they hear is coffee causes cancer. No, wait, no, coffee prevents cancer. No, wait, it causes cancer. No, it prevents cancer, right? So, this joke, you're in a taxi and something comes on the radio, says, chocolate's bad for you. The taxi driver says, oh, wait a week. They'll come up with a study that says it's good for you, right? That's where this comes from, is by trying to say that we have the answers and there's no uncertainty. And I think we really need to educate the public in how does this actually work. Very interesting discussion about our own incentives and conflicts of interest, and how, as communicators of science, whether you're the scientist communicating about it, you're a public information officer, you're a journalist, we need to understand our own incentives and problems therein, as well as those of others. So the journalists talked about how, for them, when they're evaluated by their editors, one of the main evaluations is how many times people click on their article, much web traffic they get. And they admitted that can drive them in a certain way. Right? If you think this is going to get a lot of clicks, you're going to maybe do it because that's going to be good for your bottom line. And finally, there was a lot of discussion about press releases. So beware of press releases. And that's not to say that press releases are inherently bad, but I can say, based on what I saw coming across my desk and what the journalists said, there are way too many of them being written. Okay? And let's try to keep them focused on the things that really are important and where we really can say something and not just be throwing them out the door, because it's not helping anyone. The journalists there was one from Science and one from Nature, and and I asked them straight out, how many press releases do you see a day, and do you use any of them? And the answer was they see hundreds a day. So they said hundreds, and they don't use any of them. I would just be a little cautious then in terms of that. So that's what I had to say. Again, congratulations to everyone who won an award and everyone who was nominated. I think this was really a neat event, and clearly great things are going on here, and I think you should all be very proud of what's happening. So thank you all very much. Oh, sir.
The director's program, the DP5 program, to sort of skip the postdoc. Do you know enough about whether that's working, and what do you think about those kinds of programs?
So there's some early. Okay, so the question is about
what we call the Skip the Postdoc Award, the DP5, which allows people who are deemed to be sort of at a point after graduate school where they could actually go straight into an independent career to do that. So it's kind of a bridging award to allow them to do that. There are some preliminary outcomes data. They're a little conflicted on how well this is working or not. So I can't give you definitive answers. You know, I think it's going to be one of those things that in some rare cases it can work. In probably the majority of cases, it would be better to gain a little more experience and a little more mentoring before you embark on an independent career. There are other awards that are a little bit later, like, as you probably know, the DP2, the new Innovator Award, for someone doing something particularly innovative, but at a more traditional independent stage. That's the best I can do at this point. But they are watching it as it goes along.
Do you have an opinion about preprints and whether they're going to be helpful or harmful to people establishing their careers?
Yes, Judy asked about preprints and whether they're helpful or harmful.
That's been a big discussion both at NIH and elsewhere in the community. So Ron Vail set up this ASAP Bio organization, which is actually having a second meeting in February, which I'm going to. I've started putting up preprints of all of our papers, all being a fairly small number at this point. But I think it's a very attractive model myself. I think that anything we can do to improve the flow of scientific communication and to open up the process is good. The worry, of course, when you put up your work before it's been accepted in a peer-reviewed journal is somehow somebody else is going to scoop you and steal it. This has worked in physics for many, many years, and that has not been a problem. You know, I guess if you're in a particularly competitive area, maybe you want to hesitate on that. But I see this as a model that could grow as well. That if what we could get is for people to routinely start commenting on preprints, giving people feedback at that stage, it could really improve the scientific process, right? If that could become sort of the main mode of communication, where you put up your preprint and that's what people read and they gave you comments and then you put up a revised version eventually. That could be transformative in how we interact with each other and how we communicate.
I think it's very important to be able to disseminate negative results, things that don't work, because otherwise people's thought processes are off target, a lot of time is invested, and a lot of financial investment.
Yes, I agree. So the question was about negative results, the importance of
putting them up. I completely agree. And preprints are a good way to start doing that. If you have a negative result, you can write a preprint and put it up. There are journals now that I think, PLOS ONE will take work as long as it's scientifically sound. So at some level, there's not that much excuse for not publishing them. Where it's particularly important is in the clinical arena, right? NIH was shocked a few years ago when they did analysis prompted by a group in England and found that a very large fraction of NIH-funded clinical trials were never published. And that's very disturbing. And many people said, well, the results were negative. But as you say, we need to know that. The public needs to know that, and you don't want to do it again if it was negative, because that's a tremendous waste of money. And the negative result can be important, too. I think that's important. Sir?
On R1 is $250,000 that was established in 1998 based on the average of NIH budgets or R1 budget at the time. So an R1 hasn't gotten a raise in about 20 years. And if you do the analysis of how much everything else that an R1 pays for has gone up, the R1 modular cap now should be about $475,000. So, and this goes to some of your comments where you said people should be spending more time writing grants and doing grants. Has there been any talk about revisiting the modular cap? And I understand that you don't have to ask for a modular budget, but there's the reality of what goes on in there.
The question is about
The modular cap, which has been $250,000 for, what, 20-some years. So there's been a lot of discussion of the possibility of raising the modular cap. One thing I will note is we did analysis of our own portfolio, and although there has been a loss of the average grant budget to inflation, it's not nearly as dramatic as inflation as a whole. So people have increased it by not asking for modular or going higher in modular. And that's somewhat kept up with it, more than people think is true. The reason that we haven't moved forward with increasing the modular cap is that graph I showed you with the disparity of funding. Because as we started talking about it, we realized that if we didn't deal with the disparity of funding issue, raising the modular cap could well exacerbate it. So we didn't want to do that until we had dealt with how do we try to improve the distribution of funding. Because what we were worried about was it wouldn't actually help the average scientist that much. What it would do would be that the people who had 3 grants would still have 3 grants, they'd just be bigger. And since the budget wasn't getting any bigger, you can see where that's going, right? That's been our concern.
Actually, a related question has to do with stipend support for graduate students and postdocs. It's not much better for postdocs, but the level of stipend support for training grants and things like that is actually well below what the stipend levels in most places. So is there any thoughts, especially as you're rolling out the new plans for training grants, of bringing those into being more competitive with the actual marketplace?
we've
Raised it, recently. It gets raised a little bit, usually every year, a little bit, I know. Again, it's a question of, do you want fewer slots for more money, or do you want, a larger number of slots, and then have institutions put in the rest? And it's a debate. I mean, you could be on one side or the other of that debate. We tend to have chosen to say we would prefer to give somewhat more slots than to give fewer, because it's a zero sum. So if you're going to increase it, it's not that money magically comes in and we increase the slot, the stipend level. It's that we cannibalize other slots in order to increase the remaining slot stipend level. So that's the trade-off. What we have been focusing on is actually the health insurance side of that, because what we have is way below what, say, NSF has. So we've been trying to help with that, which we see as a significant problem.
University campus, so on. Breadth and depth of knowledge and historical context. Today, PhD programs have changed away from the traditional model, which most of the Nobel laureates talk about grew up under. So what do you think the impact is of this new model for graduate education in terms of not paying much attention to historical data, not training them as first and foremost scholars, but rather as most technocrats to accomplish scientific goals because they're viewed as cheap labor? How do you think in the long term that's going to impact the scientific enterprise in the way?
well, I guess you have to accept the premise first that it is very different.
When I look back on graduate education, what I would conclude is that it hasn't changed much over the last 40 years. What I perceived, and I think many others perceived, is that there is an emphasis on teaching facts. I put facts in quotation marks because they probably won't be facts tomorrow. So if you want to have an emphasis on, you know, the arc of a field and the tried and true, I think that's something that should be continued to be incorporated. If what your plan is to teach students the name of every translation factor and transcription factor that, you know, was discovered yesterday, I think that's not going to be productive. And so what we've tried to do in this new T32 funding opportunity announcement that Charlie alluded to is to steer people more towards what we're calling skills. But I don't mean skills as just, you know, can you use a pipette? I mean skills as, can you design a good experiment? Can you interpret the data strongly? Can you communicate the results in an effective way? Which I think probably was more of what was in graduate school 50 years ago when there weren't as many facts. And I think at some level maybe what you're reacting to is that the ship has started to capsize because there's just no way you could use a model where you're trying to teach somebody everything that is supposedly known. And maybe I'm wrong. What is replacing it?
Teaching, as you said, techniques and basic fundamental principles that are applied to whatever you're doing in the laboratory rather than a broader breadth and depth. So that, for example, the Cisplatin story, that individual had a breadth of information that allowed him to be able to integrate that information. And today I would suspect that many people wouldn't have that breadth and depth of knowledge to integrate that information.
And I think, maybe, to me, confusing two things somewhat was what you teach first-year graduate students versus the accumulated knowledge one gets
studying in one's field. So Rosenberg was an expert, you know, as a professor, as a scientist in bacterial cell division in general. He had developed that font of knowledge through his own studies. Whether or not he learned it in graduate school, I doubt, right? Because he was there as it was happening and evolving. So I think those may be two different things. He was a great scientist, first and foremost, right? He thought to do the control, which was to change the electrode and not to accept the, what appeared to be an amazing transformative result right away. So that's what I would argue we want to be teaching the students, is how to think of that control that's going to actually completely change their understanding, which is not something that you can memorize. Right?
We need to wrap up. Let's have a terrific hand for Dr. Lloyd.
Thank you all.